Thank you. Hello, everybody. My name is Salih ERGÜN. I'm the CTO of Erarge. Initially, I would like to express my thanks to Ali Serdar, AI for Sec and Talintech University for hosting this organization. Today, I will present past, today, and future of cybersecurity solution for electrified automotive. So, Erarge is a research-oriented SME working in the following fields that form smart cyber-physical system for 50 years. These files are industrial electronics, embedded system, multimedia system and application, nonlinear system and circuits, cryptography and information security. So we have 12 PCT patents in various domains. We have more than 200 papers in top journal and proceedings. And we have 3 international best paper awards. 2 of our ITEA projects are also awarded. One of them is most innovative project, and the second one is the most innovative project, also in 2021. So you see the past, today, and future perspective of automotive industry. As you see, in the past, from the connectivity perspective, there is no or limited connectivity. There is no gateway in the past. But today, we need high-speed wireless interface. From security perspective, there is no or limited security. But in the future, we need high security. We need isolation, public key crypto system, consensual firewall, and intrusion detection. From the processing perspective, there is no routing in the past, but in the future, we need advanced routing, vehicle auto analytics, EQ consolidation, and services. From the networking perspective, in the past, there is limited bandwidth, but in the future, we need high bandwidth and scalable architecture. And from this functional safety perspective, it was up to ASIL-B with fail-safe, but in the future, it's going to be up to ASIL-D with fail operation. So in the bottom, you see the past E2E architecture. There is no gateway, but in the today and trending topics, there is domain centralized architecture. There are some domains, and basically, Tesla proposed a new system. They proposed to use a central processing unit, and this is the future perspective. There is a one the central processing unit, and there are multi-domains together with gateways. So we need to focus on cybersecurity regulation. There are a lot of regulation we need to consider. So these are Cybersecurity Act, Cybersecurity Guidebook, Cybersecurity Engineering, and the basic standard is ISO 21434 we focus on. There are also some United States and Japan-oriented standards for automotive. Besides the automotive cybersecurity regulation, we need to also focus on V2X and general cybersecurity regulations. So from the data protection, cybersecurity, and software update, we need to determine the security aspects. Then in the second step, we need to do threat analysis and risk assessment, and we need to construct the table of threats. Then we need to define mitigation principles, and finally, we need to develop recommendation on cybersecurity. So there are some goals from the organizational level and also design level. From the organizational perspective, vehicle manufacturer requires a cybersecurity management system, and vehicle manufacturer required to certify the compliance for cybersecurity management system. Then there are some requirements for cybersecurity and also obligation to manage supply chain. From the design perspective, there are requirements for vehicle types, and also we need to do modification and extension of vehicle types. And as I said before, we need to do thorough threat analysis and risk assessment and mitigate principles. So vehicle manufacturer responsible for overall vehicle architecture and aggregation of system supplier information, system supplier responsible for the documentation of supplied system and aggregation of supplier information, and sub-supplier responsible for the documentation of supplied components. And at the technical inspection, they do the checking document and advocate type approval. So to sum up, we need to do organizational cybersecurity management, project-dependent cybersecurity management, and we need to do distributed cybersecurity activities. There are also continual cybersecurity activities, which are divided into concept development, product development, and cybersecurity validation. At the end, we also have a post-development phase. And in parallel to cybersecurity management, we also need to do threat analysis and risk assessment. So cybersecurity incident cause vulnerability, vulnerability cause weakness, weakness cause cybersecurity event, and as a result, we have a cybersecurity information. So at organizational level, there are governance concerning rules, processes, resources for product cybersecurity. And at the organizational level, there is incident response referred to evaluated activity of organizational facing a cybersecurity incident. And we need to aware and and we need to have a cybersecurity culture at organizational level. At project level, design level, we need to plan and tailor of cybersecurity activities and various type of products. Cybersecurity case, evidence of cybersecurity engineering for a product, and at the cybersecurity assessment, we need to judge for the specific product. At distributed activity, cybersecurity interface agreement for customer-supplier relation covering the phase of product life cycle must be done. So there are both organizational measures and technical measures. Organizational measures are divided into general measures, secure development measures, and security until the end of automotive measures. And technical measures are divided into communication protection, self-protection, cryptography, user data protection, identification, authorization, authentication, and security audit. So to do the threat analysis, threat analysis and risk assessment, we use Stride and Lindum privacy security threat modeling for creating a risk map and related requirements. We also use ENISA and MITRE. Based on ENISA and MITRE cyber physical threat taxonomy, security requirements and test routines are determined. And finally, as a result, we determine the physical threats, the match, the unintentional and intentional damage scenarios. And as Erarge, we built up we have a digital transformation strategy. We built up technology and innovation by bridging information security, industrial, electronic, and innovative software technologies. And we are aiming to digitally clone automotive system or subsystem into these files for the sake of better connectivity, safety, and security, accountability, and efficiency through hardware-software integration. We use artificial intelligence, chaotic prediction methods, and big data, and we focus on actually the security part. And we designed the digital twin of security part. So basically, there are two regulations, and these are mandatory for all automotive industry. So these are mandatory by June. Actually to the end of this year. So these regulations are R155 and R156. We do thorough threat analysis and risk assessment, and we basically focus on ISO 21434 standard, and our solution portfolio meets the requirements as a countermeasure against cyber threat addressing ENISA and MITRE. And as a result, from past to today perspective for automotive industry, we propose secure canvas authentication device. So this is enough for past to today automotive industry. So from today to future perspective, we also design a secure gateway family for point-to-point secure communication on vehicle part. And at the center, at the heart side, as the core part, we design a hardware security module, which have two versions, PCI HSM and network HSM version. And this hardware security module is used at the server side, not only used as a key generation, key distribution or device, but also used for the encryption and decryption at the center side. So from past to today perspective, we already designed a CAN authenticator, as you see in the figure. In this design, we consider that a bus, a car is as a black box is secure and no one can probe this black box. Only the port that can probe or that can reach outside the world is only the OBD2 port, service port. And we mount this CAN authenticator device to the service port. At the server side, we have a HSM. HSM generate the certificates and also distribute these certificates to the CAN authenticators. And after successful secure authorization and authentication, then the service person can only reach the service port, but otherwise no can reach the OBD2 port, service port. So this is a solution from past to today perspective for automotive industry. So from today to future perspective, we already design. We also collaborate with Ali Serdar Bitnet and Autocar, and we are designing new generation electrical and communicating autonomous vehicle. So in this design, we offer end-to-end holistic cyber physical security platform for autonomous vehicles. We integrate with secure fog computing infrastructure, and we also design digital twin based on dynamic modeling and strengthening the autonomous driving security against cyber physical attacks. So in this design, we propose to use our secure gateway. So at the client side, we also use a FIDO compliant user authentication token to access V2V framework over web. And at the client side, we design a secure gateway, hardware secure gateway, and we use it at nodes to encrypt and transmit, receive the IoT data. And at the server side, we have a hardware security module, which generates crypto keys, also certificates, and which is used at the server side to encrypt and decrypt the data coming from the client side. So for the future perspective, we also focus on the electronic components IC design. So we already designed high-speed true random number generators, which is used for crypto key generation. We not only design and implement these true random number generators, but we also crypto analysis and offer some vulnerability analysis methods. So there are four fundamental techniques for random number generation. These are amplification of a noise source, dual oscillator architecture, continuous time chaotic oscillators, and discrete time chaotic maps. We are aware of all these four main methods, and we design random number generator both based on both four methods, and we also propose crypto analysis method. So we focus on FPGA-based random number generators. So there are two types. One of them is chaotic system-based FPGA random number generators. So we construct the digital twin of random number generator. Target system is the physical part, and clone system is the digital twin part. So we probe only one node here. So this chaos-based random number generator use a continuous time chaotic map, and there are some chaotic variables, and we probe only one variable. We probe only one node which corresponds to one variable. And at the right up corner, you see the revealing the secret parameter of chaos-based random number generator. Although we don't know the secret parameter, we can reveal this secret parameter. So we construct the largest conditional Lyapunov exponent against condition coupling strength. When the coupling strength is negative, identical synchronization is possible. You can synchronize the target system at the clone site, at the digital twin part. You can reveal the secret parameter, and you can also synchronize the target system. At the right down corner, you see the experimental verification of this cryptanalysis method. We also experimentally verified that, not only numerically, but experimentally verified that you can identically synchronize to clone system, and you can reveal the secret parameter, but not only reveal the secret parameter, but also you can also generate the crypto key at the digitally cloned part, at the digital part, the digital twin part. So there are also some innovation offered by our company. So not only the crypto analysis, but we also design a dual core secure processor with RISC-V architecture. As you see here, there are two dual cores. One of them is red core, the other one is a black core. So there are also redundant crypto accelerator. So this is dual redundant core processor. So we offer automotive security from chip level to system level. So instead of a single core processor, it's better to use a redundant dual core. So for side channel attack, we also propose to use a chaotic clock instead of a periodic clock for driving a processor. So it's robust against side channel attack, and it's also suitable for EMC compliance. We integrate our high-speed to random number generators on silicon, and we not only design but also crypto analysis and make more robust against known attacks. And finally, everything that we propose here can be integrated with digital product passport. So with the research for decentralized industry 5.0 society 5.0, strengthened with IoT-enabled and AI-powered blockchain ecosystem. So I try to present not from a academic perspective, but industrial perspective, since our company is responsible for the industry part. Thank you for your attention. So I can answer your question if there are any.
Thank you very much. Any questions from the audience?
Yes, so maybe I come to front because then it's better here. So yes, thank you for a very nice presentation. The question about this dual core processor. So what is the status now? And so we are also like starting some project with ETH Zurich and Maxim Janichin, our colleague, so on RISC-V processors and reliability mainly. But it sounds a really interesting product idea. So what is your status, and if you plan to make a chip or IC out of it or as a product, or is it more like a core, and how is it going?
So actually, this is one of our old idea. We already designed and implement a single RISC-V core in Turkey. Then we also implement a 4-core version. We implement at TSMC 65 nanometer a single core processor. We already designed 4-core version at FPGA level. So as you know, we already designed a hardware security module, and hardware security module includes all crypto algorithms, hash algorithms. So we already implement this at FPGA level, and maybe Alper will give you some detailed information for this project. So we have a project together with Baran Hoca. So
Yeah,
we
the
also
next art project.
yeah. So in next art, so
Okay,
in that
yeah,
project,
yes.
we already proposed this idea. So we have implemented this at FPGA level, but I mean we are open to collaborate with ETH Zurich because in pilot 2, I was also responsible for establishing the VLSI design center at TÜBİTAK. So I already established a center at TÜBİTAK in Turkey before, and our team already designed a single core processor at TÜBİTAK, and also we collaborate with ETH Zurich at Pilot 2 project. For now, I mean, we already sent this project to Chip Act, and it gets a high score in the first round. Yes, Alper, so you may contribute. So, I mean, we are open to collaborate. We can integrate this in another project.
In short, at the FPGA level, it has been implemented, but we need some funds for the prototyping. So we are really open, and I hope this project will also help us to come up with a prototype.
Yeah, and as a comment, that Altec is also partner in NextArc, so we are trying to push it for funding. So let's see.
Perfect.
Yeah. So
hopefully,
Any question? We can also continue in the brainstorming session.
Yeah.
Okay. So
thank you so much.
Thank you, John.
So let me